So, next example is electronic switches. Now, electronic switches we will be using to connect a line or to isolate another line, and not that before electronic switches we did not have this type of applications, we have some other alternatives also. So, let us first discuss what are the basic characteristics of these different types of techniques which are used to isolate input and output. The first example here, it is based on circulator. So, in this typical example, one single antenna is connected to transmitter side and the receiver side, and now when this signal from transmitter side it goes to circulator it directs the signal to antenna, and if any signal is received by antenna, then circulator it will directs in the same direction to receiver in a clockwise direction it is showing. So, that is how we can isolate receiver and transmitter. So, at any time communication is possible, or it is a full duplex system. Next, this is one example of duplexer. So, here diplexer or duplexer, it is formed by using filter bank. One frequency is used for transmission and another different frequency is used for reception. So, again it is a full duplex system and it can isolate transmitter and receiver at any given time. And the third example is by using switches. So, in this case we can see that the single antenna it is connected to transmitter side or receiver side, and this connection depends on the state of switch. So, two important characteristics then it should have: very good isolation between the input side and output side, or receiver side and the transmitter side, because transmitting power it is very high, it can be of the order of a few watt, and receiver side typically received power it is of the order of nanowatt or even less than that. So, there might be very good isolation between the transmitter to receiver, otherwise there will be leakage. And also when the switch it connects one line, let us say transmitter to antenna, it should provide very low insertion loss. So, this low insertion loss and high isolation, they are the characteristics of any solid state based switch. Also we see that it is not a full duplex system. When we are using the antenna for transmission, we can't receive any signal because the receiver path is open. So, here are a comparison of the advantages and disadvantages of these three different types of technologies. Circulator, we have load pulling protection. So, right hand side whatever you connect, whatever impedance may be, it does not have any problem to left hand side, but it has the disadvantage that it is bulky, because it is made of some ferrites device. So, it needs biasing arrangement, it needs some magnet. So, that is why it becomes bulky, expensive, and typically this is also a narrowband device. So, next is duplexer. Its advantage is its linearity. So, whatever power we use, low power or high power, it won't give you any non-linear property. So, this is the main advantage of a duplexer, and also it allows full duplex system. But the disadvantage is that we have to design two band pass filters having two different frequencies, and now let us say two frequency bands, they are closely spaced. So, then the rejection level at these two bands for these two different filters should be as high as possible. Sometimes the specified value it can be 80 dB or more. So, from filters theory already we have seen that then we should use very high Q resonators to design this narrow band filter with very high attenuation rate. And if we go for very high Q or low loss, then we have to increase the size of the filter and it would become very bulky and expensive. Next, switch, it is highly scalable. In fact, it is possible to fabricate inside any integrated circuit in VLSI technology. We can fabricate hundreds of switches together, but main problem is its linearity, because in most of the cases it would associate it with some PN junction or even let us say Schottky diode, and all of them are associated with some sort of non-linearities. So, typically if we go for high power applications, in that case it will generate harmonics and signal itself it will be distorted. So, linearity is a big problem for this type of switches, and not only that, we also have to provide biasing arrangement and the control signals. Already we have seen for the pin diode sometimes how problematic it can be. So, biasing current also it can be very high, typically sometimes tens of milliampere. Now, in a system if we have hundreds of switches, so you can imagine how much power it will consume. So, in this class we will mainly concentrate on different types of electronic switches. So, because of their advantages, compact size, and since they are highly scalable, but already we have seen the disadvantages that we need biasing circuit, control signal, and linearity is a problem. They are typically used in MIMO structure, TDMA systems, phase shifters, array antennas, voltage controlled oscillator, etc. Here it is a schematic example of a MIMO system. We are using two antennas and we have different receivers and transmitters. So, we are using multiple multi-throw switch here, and that will connect to one antenna to one receiver side or one transmitter side depending on requirement. So, we are using a switch bank here. Another example, this is a passive component Butler matrix. It is used for phased array antennas. Inside the Butler matrix, we have a combination of several branch line couplers, passive phase shifters, crossovers. Now, the order of the Butler matrix, it is 2 to the power n by 2 to the power n. So, we have 2 to the power n number of input lines and 2 to the power n number of output lines. Now, antennas, they are connected to this all output ports, and the RF input at a time it is connected to one of these 2 to the power n input by using a switch. Now, how it operates? Okay, so, let me just discuss a few basic points on phased arrays. So, let us say we have one 2 antenna system, and this first antenna is connected to a phase shifter, and the second antenna we are using as the reference antenna. Now, the resultant beam direction, it is in broadside direction when the phase difference between two antenna feet is 0. Now, if we introduce a phase shift between these two antennas, then beam direction will change, and this change or new beam direction, it depends on the phase shift value. So, for an arrays of n antennas, if we assume it is a linear array, In that case, we have to maintain the same progressive phase difference between successive antennas to direct the beam in a particular direction. Now, if I go back to Butler matrix, so for Butler matrix, when let us say the input is connected to the first input, then we have a typical phase distribution, and because of that we have a progressive phase shift between the output points. If the input is connected to second point, then this progressive phase shift will change and the beam direction will change. If we connect to third input point of the Butler matrix, then again we have a new phase distribution among the output points. So, we have a new beam direction. So, that means for a 2 to the power n input or 2 to the power n output lines, we have 2 to the power n possible beam directions, and at a given time the actual RF input is connected to one of the input ports of the Butler matrix. So, we need a filter bank at the input side to control the beam position. So, these are some examples of application of electronic switches. Now, switch specifications. For small signal case, the main characteristics are insertion loss. So, this is the loss between input and output, reflection loss seen at the input terminal, isolation when the switch it is off, we are expecting very good isolation between input and output, and then the bandwidth of operation. But when we go for large signal high power case, in addition to all these points, we have to consider some extra points. One, for example, what is the highest power handling capability? Next, what distortion it produces? Then what is the 1 dB gain compression point? If we keep on increasing the power, then output power at some point can decrease. Then what is the effect of intermodulation? So, since because of the non-linearities, we may have distortion or intermodulation effect, and why it is so important? Because it can generate some other frequency components which can interfere at the receiver side with. So, we have to be very careful about these points when we go for high power applications. Now, different types of switches according to the number of points to which the switch is connected and the number of points where it can connect. It can be named as single pole single throw switch. In this case, the switch is connected to just one point, or it has one pole, and only one switching position is possible, one single on or off, or we call a single throw position, or simply SPST switch. The next one is single pole double throw switch. So, switch is connected to one point and it can connect either the first line or second line. So, two throw positions are available, we call it SPDT switch. In general, we can define alpha pole beta throw switch or alpha P beta T switch. Now, small signal model of a switch. Already we have seen that a pin diode or a Schottky diode we can use as switch. Typically, PIN diode is used at low frequency operation and switching speed is low, and Schottky diode used for very high frequency switching. Now, when the diodes are in forward biased condition, in simplified form we simply represent by them a resistor, a small value of resistor, and when they are in reverse biased condition, we replace the diodes by a small value of capacitor. So, this capacitor value and the resistor value, it is defined by the companies. it depends on fabrication procedure and the materials they are they are using. Now, how to connect these switches in practical applications? We can connect them in series configuration, we can also connect them in shunt configuration. In the previous example, we used the pin diode in shunt configuration. So, in shunt configuration, when the pin diode switch is on, that means we will be representing the pin diode by a small value of resistor, then it will be simply RF signal, it would be grounded. So, let me draw a diagram better. So, let us say we have a microstrip line, I am showing just the top view of the microstrip line, and this left hand side is the RF in point and right hand side this is the RF out point. Now, I am using a switch in series configuration, in shunt configuration. So, it is connected between the microstrip line and ground. Now, when the diode is on, in that case we can represent the diode by a small equivalent resistance R on. Typically, R on is just a few ohms. So, in this case what will happen, since the resistance is just a few ohm, so RF signal whatever coming from left hand side, it is grounded through the resistor, and we have very good isolation between the input point and output point, since we do not have any microwave signal or millimeter wave signal present at the output. Now, consider the second scenario, when this diode it is switched off. In that case, we can represent the diode by a small value of capacitor. So, C typically a few picofarad. So, in that case, since it is a small value of capacitor, so equivalent reactance will be very high for the RF signal, and the whatever RF signal we have, it will simply pass from left hand side to right hand side, or we have direct connection between the input and output. So, this is in shunt configuration. We can use the same diode in series combination as well. So, in that case the switching condition will simply change. So, how to connect in that case? We have the same microstrip line, but now we are using diode in series combination. So, we have RF in left side, a load maybe RF out right hand side. When the diode is switched on, we will be representing the diode by a small value of resistance. So, when the resistance is connected, since it is a very small value, it will connect simply left hand side to right hand side. So, R on in series, it will give you some insertion loss, and we see in this case left hand side is connected to right hand side. You can compare this situation with the previous one, and we have transmission from left to right, just opposite what we have seen in previous case. Now, let us say the diode it is in off condition. So, we will represent the diode by a small value of capacitor here, and since we have very small value of capacitor, it is associated with very high reactance, and we have high impedance as seen by the RF input port. We have input reflection from this capacitor, and we have very good isolation between the input and output point. Now, the question is that let us say one type of switch is given, it can be one pin diode or it can be one Schottky diode, then should we use in series configuration or shunt configuration, which one should we prefer? Then we have to do some analysis, and after analysis the conclusion is that in shunt configuration, if I use a single diode, it would provide better isolation compared to that in series configuration, considering that the shunt capacitance typically a few picofarad and on resistance is a few ohm. So, how we do the analysis? So, let us see, we are considering SPST switch. Let us first consider series configuration. So, as I discussed, it is modeled by a resistor in on state and by a capacitor in off state. So, in on state, then looking at the circuit whatever I have drawn previously, we can easily calculate what is the S21. So, if I go back to my drawing, so we can consider it as a 2-port device, right, where we have port 1 here, port 2 here, and this is a section of transmission line, this is another section of transmission line, and in between we have a resistor connected to ground. So, simply by multiplication of ABCD matrices and then converting it to S parameters, we can calculate what is the S11 and S21 of this arrangement. Obviously, when we implement any switch, there won't be only one single pin diode or Schottky diode. In addition to this, we should have DC blocking and RF blocking arrangement, and for that we have some additional capacitors and inductors, but at RF frequencies those capacitors or inductors will be representing by short circuit or inductor by open circuit and capacitor by short circuits. So, not only for this case, for the second case also we can calculate what is the S11 and S21. So, let us say the port impedance, it is given by Z0. In that case, when the switch is on, we are considering series configuration now. So, in series configuration, when the switch is on, left hand side is connected to right hand side, and we replace the switch by a few ohm resistor, which is R on. If you calculate S21, that is equal to in dB 20 log 10 of 1 plus R on divided by twice Z0. And in off state, that means when the switch is replaced by a small value of capacitor, if I calculate S21, so isolation I series, that is 10 log 1 plus 4 pi f c of Z0 whole to the power minus 2 in dB. So, we have actually one half term, one square term here, because of that the 20 log it becomes 10 log. So, a typical example for a maximum insertion loss of 0.34 dB R on equal to 4 ohm. If I look at the expression, insertion loss it depends on R on, isolation it depends on C op and operating frequency. So, if I increase the operating frequency for a given switch, will what we expect? Decreased isolation, because capacitive reactance it decreases with increasing frequency. Now, let us consider shunt SPST switch. In this case, we are using the pin or Schottky diode in shunt configuration. So, in on state, now we have to replace the diode by a capacitor. That means, in this case left hand side would be connected to right hand side, and we call the switch is on, but the diode is off, and S21 or insertion loss in shunt IL shunt, that is equal to 10 log 1 plus pi f c of z naught whole to the square in dB, and in off state isolation I shunt 20 log 1 plus z naught by twice R on. So, we see here now insertion loss, it becomes a function of frequency, whereas the isolation it is a function of R on. So, for very high frequency operation we have to be careful depending on the values of R on and C off, we can choose a proper circuit implementation, proper implementation scheme. It can be series or it can be shunt. So, already I discussed that for a few picofarad capacitance and considering that a few ohm are on, mostly in shunt configuration these switches provide better isolation. So, here are some examples. We can design SPDT switch by using SPST switch. Here the example is shown here. One antenna, it is connected to transmitter side and also receiver side. So, depending on the switching condition, we can direct signal from transmitter to antenna or antenna to receiver, and this is the right hand side, it shows the simplified equivalent model. We are representing the on condition by R on and off condition by C off, and transmitter side. So, at millimeter wave frequencies or even at microwave frequencies, if nothing is specified, it is 50 ohm system, or left hand side, that is why it is represented by a 50 ohm, right hand side it is also represented by a 50 ohm load. Antenna input impedance when matched, that is also 50 ohm. Now, how to improve the isolation for a given switch, because it is a problem at higher frequencies. A pin diode, let us say it is providing very good isolation of 40 dB at 1 gigahertz. If I use the same pin diode above 30 gigahertz, isolation it can degrade to just 2-3 dB. So, isolation improvement it is a challenge for any given switch. So, next step, if we have 2 pin diodes or 2 Schottky diodes, we can use them in series shunt configuration to improve the isolation value. So, what we will be doing here, let us say the switch we want to use in series shunt configuration. So, one pin diode we will be connecting in series configuration, another one in shunt configuration. Okay, so, let me draw it. So, this is the microstrip line top view. One diode will be used in series configuration and the second diode will use in shunt configuration, and together it behaves as a single switch, SPST switch. Now, if I want to connect left hand side to right hand side, then what should be the conditions of the diode? I want to connect left hand side to right hand side when the switch is on. So, in on condition, this diode it should be replaced by a resistor R on, small resistance value. So, this diode should be in forward biased condition, and this diode it should provide good isolation. So, we should represent the diode by capacitor C off, or the second diode it should be in reverse bias condition. Then in off state, this is just opposite. In off state, then this first diode it should be in reverse biased condition, and the second diode it should be in forward biased condition. So, we have isolation due to first diode and further isolation for the second diode. That is how we can improve isolation here, but insertion loss it will degrade. But anyway, for any practical applications, we mainly look at the difference between the insertion loss and isolation. So, now again if we calculate S21 for this case, in on state insertion loss or S21 is given by this expression, it now becomes a function of both R on, C off and frequency, and isolation or the switch is off. In that case S21 is equal to 10 log of this function. So, it is also a function of frequency, capacitance and R on series resistance. So, for any given switch, how good it is to understand that we defined a parameter, we called it figure of merit for a given first order switch R and C. So, this is simply R on multiplied by C off, just like one RC circuit, the unit is second, time constant, but R in on state, C in off state. So, smaller is the figure of merit, bigger is the switch. Here are some comparison. So, insertion loss versus frequency for different figure of merits. So, we see that for 25 femtosecond R on C off, at even 140 gigahertz the insertion loss is below 1 dB. For 200 femtosecond it degrades to almost 4 dB. We have considered R on equal to 4 ohm. Now, right hand side figure it shows the variation of isolation. For 200 femtosecond, you see at 30 gigahertz isolation at least we have 7-8 dB, but at 140 gigahertz it is less than 5 dB. We do not have any isolation. If we go for much better switch 25 femtosecond, let us say, in that case at least we have 13 to 15 dB isolation at 140 gigahertz. So, isolation, insertion loss both depends on figure of merit R on into C off. Okay, so, next day we will continue, we could not finish the switch here. So, next day we will continue another 10-15 minutes on switch, then we will start the millimeter wave propagation part. Thank you.